Okay, here we go. So N is the index of refraction. Okay, and so N is a ratio. It's a unitless number because it depends on the ratio of two speeds. C here is the same C that it has been, which is the speed of light in a vacuum. This is 3 times 10 to the 8th meters per second. So you can see that that number is a constant on the equation sheet. V is the speed of light in that material. And so what we see here is this is a table of all the different indices of refraction, or a few indices of refraction of different things. And for a vacuum, it's 1, right? This ratio of C, which is the speed of light in a vacuum, relative to the speed of light in the medium, which is a vacuum, is just 1. N is very close to 1 for air. So for all practical purposes in this class, the speed N for air will be 1.00. We rarely go out more than 3 sig figs. But you can see that actually it gets bigger for water. So what this bigger number means is saying that the number on the top, C, is bigger than the number on the bottom. So the speed of light in a vacuum is faster than it is in an air. So this number, and so that's what generally happens is that as we go to denser and denser media, so we go from a liquid to a solid, the index of refraction gets bigger. Okay, and so a couple of things I was going to show you that talk about this. One of them is that actually Pyrex, which is not on this list, but it's a kind of glass, and olive oil have almost exactly the same index of refraction. And a pretty cool thing happens with this, which I am hoping to show you here. So I have some olive oil and a piece of glass here. And so when I put this piece of glass in here, find a portion of the glass where there's not writing. It goes in and it disappears. Do you see it? That piece of glass is nowhere to be found inside of the olive oil. So this is an excellent party trick or excellent quarantine trick. Your broken glass, or it doesn't even have to be broken. I had an old beaker. You put it into Pyrex. It has to be Pyrex, not just any old glass. Any old glass won't work. Pyrex into vegetable oil, and it will disappear in the oil. Oh, the reason that this happens is because light bends as it passes from one medium to another, and we can see the bending of the light, right? So we appreciate that the light has bent, and that's how we can see that transition. Right? That's how we see this piece of glass here. But if the index of refraction of the two liquids is the same, then the light doesn't bend, the light doesn't refract. So there's no bending of the light here, so it appears invisible to us. We don't see it. Another example of this is going to come from a video, which I have set up right here. And this is a Clearin optics device. And so what this is it's set up as a mirror. So that is a very precisely calibrated mirror right here. And there's a light that is going to be shined on this mirror, and they're going to use a camera to take a picture of the image from the mirror. So there's sort of just the image that is made from the mirror. And right down here is a candle. And the candle is going to warm up the air, and it changes the index of refraction of the air as it warms up. And so you can see that actually the photograph that the camera is taking of that mirror shows the convective plumes coming up from the candle, because as light passes through that hot air compared to the cold air, light travels different speeds and different temperatures of air. So pretty cool. This is also exactly why you see mirages. So, oh, there's a hairdryer. So this is why you see a mirage. So when you look in the distance on a hot day, the surface of the ground is hotter than the air above it. So light bends differently really close to the ground, and you'll see different images near there. Nice. You could watch things like this all day. So that must be hot air in that balloon that is coming out of the cup. Oh. So this would be a liquid that has a different index of refraction than air. So the light is bending differently, not because it's a different temperature, but because, oh, that is a gas, not a liquid. So it's bending because it has a different index of refraction, not because it has a different temperature. Well, because it's a different material. Now we're going to dump it all out. Okay. Okay, so I hope you understand the principle of refraction. And right, here's a little video or a little picture of what we did. So we made this. We weren't really able to see this refracted ray, but we were able to see all of the other ones. So the formula that goes for the relationship between these this angle of incidence, which we call as the ones, and the angle of refraction, which are the twos, is this, okay? So the theta 1, right, the angle of incidence, and we measure that theta the same way that we've been measuring theta for this whole unit, which is that we measure the angle relative to the normal. So here's air down up here, here's water down here, and here's the interface between air and water. So our normal line comes out like that, and we measure the angle of incidence right there. So we'll call that angle of incidence. And this angle right here, theta 2, is the angle of refraction. And N1 is the N value for the incident ray, and this is the N value of so this would be air and water. Okay, and a rule that would be good to memorize is that light moving into a slower medium, so here is light moving into a slower medium, will always bend toward the normal. Okay, so this angle right here is bigger than that angle right there, and that will always be what happens. Light moving into a faster medium, so that's this one, right? Light has started in water and it's going up into air, will always bend away from the normal. So here's this angle of incidence, and as it passes into the air, it gets bigger. Okay, so we can say that N1 sine theta 1 equals N2 sine theta 2. So you need 3 things here to be able to solve for the fourth. A way that I remember this is by thinking about what happens as a lawnmower passes as you mow a lawn. So here's what I mean by that. So here is my water. Here's my air. And if I have a lawnmower traveling in the direction of this ray of light, then I can think about the lawnmower as having 4 wheels, but I'm only going to be interested in the front 2 wheels. So here's my front 2 wheels of my lawnmower. And the front 2 wheels of my lawnmower, if I'm traveling like this, it's going to happen that, think about this as being sidewalk, the fast medium, and this being grass, because grass is the slower medium. It's harder to push through grass than it is through sidewalk. Okay, and so if I have one wheel in this fast medium and one wheel in this slow medium, my wheel in the fast medium is going to turn more than the wheel in the slow medium. Okay, so if you kind of go from sidewalk into grass at an angle, this wheel is going to move more than that wheel is. So the outcoming ray, instead of traveling in a straight line, is going to bend a little bit and go like that. So if I draw in my normal line, I can see there's theta 1 and there's theta 2. And I can see that my ray has bent toward the normal, which was what the rule said. But I find this, it's totally a mnemonic. There's nothing physical about why this works, but it works very well for me. So I'm teaching it to you to try to figure out how this ray of light is going to bend. We'll just think about what a lawnmower would do as it traveled from a fast medium to a slow medium. I can do the same thing if I want to talk about what this ray of light would do if I was traveling from a slow medium to a fast medium. So if I'm traveling from a slow medium to a fast medium, then I'll end up like this. And if I hit it at an angle, this wheel on the left is going to move faster than the wheel on the right. So this wheel is going to turn more than that wheel is, and this will bend that way. And if I draw in my normals, I can see that theta 1 and theta 2 look like that. Another thing, just looking at these two things while they're right next to each other, is actually the angle that is in the slower medium is always the smaller one. The angle that is in the faster medium is always the bigger one. So that's another way to kind of develop some intuition for what this will look like. So refraction is what makes half-submerged objects look odd. So this is a figure from your book. So here is this woman's foot, and the foot is all the way down here. But as this ray of light exits the foot in from water into air, it will bend, and it hits this man's eye. But then this man's eye, what he sees is he doesn't know that this light is bent. So he thinks that her foot is actually at the location of her knee. So that brings us to the idea of total internal reflection. And this is something that I demoed in the beginning of this video. But let's see some things here. So this is, right, so there's light coming down into a water tank. And it's hitting a few mirrors that are all at different angles. So the light comes down, it hits this mirror, and this light is bounced off, and then it refracts. This mirror is at a little sharper angle, and it goes like that. And it refracts out into the air. But this mirror right here is at such a steep angle that the light never escapes the water and goes into the air. Instead, it's totally internally reflected back down. So there's a formula for the, it's called the critical angle. Right, the critical angle is the angle at which, right, any bigger angle, and there will be total internal reflection. So this is the angle TIR, total internal reflection. Okay, and so sine of the critical angle is just N2 over N1. Okay. So this is the principle behind fiber optics. So this is how fiber optic cables work. Right, is that I have a ray of light, and it is always happening that this ray of light hits at the critical angle. So this ray of light will bounce off of each side and stay in here. So we can transmit with almost no data loss over really long distances through a fiber optic cable. And I have a video of this. Up here. So this man has set up a laser beam that is traveling through a bucket of water. And this is a hole poked in the tube. The water's not coming out of the hole right now because the lid is on the tube. And so you can see the laser is traveling through the tube, and now he's loosening up the lid. So now the water comes out. And you can see that, I'm going to mute this so it doesn't interfere. You can see that, right, and you can even see the laser. See the laser line? It bounces off. And it's sort of bouncing back and forth and back and forth. and staying inside this water. Okay, and one other thing that I should point out is that total internal reflection only occurs for something moving from a slow medium to a fast medium. We will never have total internal reflection for moving from a fast medium to a slow medium. A way that you can maybe convince yourself, well, actually, we'll do some examples of that later. So water to air will never have total internal reflection. Only, air to water will never have total internal reflection. Water to air is the only way that it would happen. Okay, so now that we've got some fundamentals about how light bends as it passes from one medium to another, we're ready to move on and talk about lenses. And lenses are going to be very analogous to what we did with the mirrors. So as light passes through a lens, I can imagine, let me zoom in on this a little bit. Okay. I can imagine what is going to go on with this light as it passes through my lens. So I'm going to do my little lawnmower trick so that I can think about this. And the reason the lawnmower trick is nice here is so that I don't have to, if I want to draw the normal, I have to draw this line that is tangent here so that I can figure out what the normal is. And then I have to figure out how to make, whether the angle should get bigger or smaller. But with the lawnmower trick, I can just sort of use my intuition, right? The glass is the slow medium. The air is the fast medium. So this wheel will move faster than that wheel will. And this will bend down as it passes through. Okay, so instead of going in a straight line like it wants to do, it's going to bend that way. Okay. And then as it passes through here, the opposite is going to happen. So now now I'm moving from glass into air. So I'm moving from a slow medium into a fast medium. And now this wheel here is still the faster wheel. It's still in the air. So this wheel is going to move more than that wheel is. And my light is going to end up bending down again. All right. So light that comes in parallel to the axis of this lens, I'll put the axis of the lens like that, will bend down toward, and actually as it exits, it's going to exit out through F, the focal point of this lens. Parallel rays that come in through a lens will bend as they go through the lens and pass out through the focal point. So this is exactly analogous to what we did for the mirror, except now for the mirror we had light pass through here and then it was reflected back and out through a focal point over on this side. For a lens, the light passes through the lens and it bends and it goes into the focal point. Okay, so a converging lens is something that results in converging of the rays. And that is what a convex lens looks like. So just like a convex mirror was a mirror that bulged out in the middle, now a convex lens is a lens that bulges out in the middle. And it turns out that this convex lens is what brings the rays together, just like how a concave mirror brought the lens together. So remember, this was our concave mirror. So it focused the light. And it always made, for objects that were far away from outside the focal point, it always made a real inverted object, unless you ended up with something very close where it made this virtual object. And actually, you can even see here the virtual object that this mirror makes is always bigger. The virtual image that this mirror makes is always going to be bigger. So that the image that the mirror is making is bigger than the image of the pencil, the actual pencil itself. And the same thing will go on here. Okay, so let's do, think about our rays that we can draw for lenses. So they're going to be the same rays that we drew for mirrors, but they're, instead of the rays reflecting back to the left, they're going to pass straight through. So ray 1 exits the object, travels through the center of the lens and out to the focal point. Ray number 2 passes through the focal point, and then it runs out through the lens and then comes out parallel. And then the third ray for a lens is the easiest ray to draw, which is one that makes a straight line. It's going to pass straight through the center of the lens and out here. And where these three cross is where a real inverted object, or real inverted image, will be formed. So I've got a lens can be used to do something like this, and let me show you a demo of what this looks like. So I have here a light bulb, which I electrocuted myself on earlier today. So I'm going to try and be a little more gentle with it. And I have a lens right here. And if you look at this, you can see that the light from that bulb will pass out of the bulb and through the lens. And if everything is right, it'll make an image of the light bulb on the wall. And so that's what I have going on here. Let's make this a little bit dimmer. You can see it a little bit better. Okay. So as this kind of moves here, there's this image that's formed on the wall. It's a fuzzy image here. Okay, so the light is going from here, passing through this lens, and it's making a fuzzy image on the wall in just the right spot. Oh, now it's fuzzy again. But right around in here, it's making a pretty sharp image of the light bulb. And if you look at this image of the light bulb on the wall, maybe you can see that this is a straight line here. This is the bottom of the light bulb. So it has made an upside down image of the light bulb on the wall. And I'm going to pick this back up with the next